your cell phone as the place where it's going to get implemented. And that's fairly typically a good place because your cell phone, what do we do with them? About the end of 2 years, we trade up. And so reliability is not particularly an issue. Your laptop computer, 5 to 7 year lifetime. If it died in 3, you'd be really upset. But when you start looking at other applications like medical electronics, 10 to 15 years. If you look at solar electronics, inverters or microconverters in that industry, they have to be able to warrant the product for 25 years. So what we do is we look at some of these new packaging technologies and we kind of say, does this work in this particular environment? And do some analysis on it to help you make decisions of whether or not to use it in your particular application. So you talked again, Bob talked about artificial intelligence in his presentation, and my wife's told me that I'm one of the leaders in artificial intelligence for a long time. So let me see if I can make this work. How do I advance with this? Just hit the plus?
I think we might have to go the old technology there. So,
Put down, yeah.
All right. So like I was saying, one of the things that we look at is where are these parts going to be used and what are the issues with the adoption of this new technology. So you've got a higher volume situation with these parts, which is fairly typical. They're the highest used component in the industry today. But the path to high reliability, and some of what Phil covered will lead into what I'm going to talk about. We've seen this before. We've gone through it with ball grid arrays. We're going through it, and we've gone through it considerably with flip chip. And what I'm going to talk about today is either a bottom terminated component or a leadless near chip scale configuration. So what can cause some of the confusion with using these parts? If you look at JEDEC, okay, in the JESD 22 series of specifications, the focus is on the die, the packaging, and typically the first level interconnects. This is going to be the wire bond, the solder bump, and all the elements of the package. The only place where you'll see a focus on second level interconnects within the JEDEC documentation is JESD 22 B113 for a cyclic bend test of the circuit board. And where does that come from? The cell phone industry. Very little interest in their area with respect to thermal cycling and long-term reliability or vibration. So IPC has tried to rectify this. They've gone and created IPC 9701. A couple of issues though. It's adopted by the OEMs, but not so much by the component manufacturers. So now you've got this disconnect in the industry. And IPC 9701 is application specific. So you have to actually tell your component manufacturer what your requirement is and define the application. And if you don't, buyer beware. So what drives the output of that? And that means that there's some increasing solder wear out in this next generation package. And so the question is in your application, is solder wear out a problem? One of the things that we've seen that ties into solder wear out, and constantly we keep getting smaller and smaller packages like these LNCSPs, is the fact that the IC manufacturers continually reduce the gate geometries on their parts to reduce the size and ostensibly to increase the speed. So you've got geometries now moving down to 14 nanometer at Intel. And one of the things that we've seen at DFR is that created a new failure mechanism that did not exist in integrated circuits 10 years ago. And that's that your ICs can wear out now. And they can wear out due to the current levels flowing through the device as a function of the voltage levels and current levels on the circuit board. But the gate geometries are smaller, so they actually are going to increase the temperatures in the devices. One of the things that we've seen when you take those devices, or any device for that matter, and package it in a bottom terminated component, is the fact that you can significantly reduce the fatigue life of the part as a function of the die to package size ratio. So if you go back again to larger packages that we've used in the past, you were back here. And so you would get, you know, say 8,000 to 10,000 cycles, but now most of these packages are coming down in this range, the 60 to 70% size. So your actual cycles to failure now is more in the range of 1,000 to 2,000, which is fairly scary. That's a 75% reduction in the ability of the package to survive a long-term environment. And that's a consequence of, you know, the size of the die with respect to the size of the package. At the same time, we've also created a situation where it's a hotter device. The part has higher current densities, it's running a little bit warmer. And if you take that, what I've done here is you can see the different points on the curve, but therefore tin lead or a tin nickel copper or a tin silver copper, they have slightly different exponent characteristics, similar type curve, but your characteristic life goes down dramatically as a function of the temperature of exposure that these devices see. So if you're going to be working in a fairly hot environment, QFN or low LNCSPs may not be the best choice. This ties back to the confusion I was talking about a little bit earlier as to how do you define whether they're going to be useful. So you might want to do some. So let's talk a little bit about these different types of packages, and you've seen some of these in Phil's presentation. You've got all the different acronyms and names. You've got land grid arrays, dual flat pack, no leads. You've got the pullback QFNs that he talked about, column grid arrays. There's a myriad of these. So kind of reiterating a little bit what he talked about, you know, I've got all the same acronyms in there. I often want to come up and speak and go through the Robin Williams thing that he did in Good Morning Vietnam, where he talked for like 5 minutes saying nothing but acronyms. But you know, it's typically an overmolded package with bond pads that are exposed on the bottom of the part. They can be in single or dual row type configurations. The part's been around for 20 years, and right now it is the fastest growing part in our industry. Some of this you've heard. They're smaller, lighter, thinner, faster, and so you get a much better functionality per unit volume. And cost is a driver, and that's why they're primarily being used. They take up less of a footprint than even BGAs, and they're less expensive to produce, so that produces just a very good need for them in our industry. Like Phil talked about, they're a small package. There's really no issues with solder printing or robotic placement. You don't have the same constraints that you have with other types of fine pitch parts. No special handling trays. These can be loaded either tape and reel, or they can be loaded from matrix trays. That doesn't drive any changes to the manufacturing process. They're easier to place because there's no coplanarity issues to deal with on the part. They actually have a fairly large pad geometry, and consequently, you know, they're less prone to bridging when proper pad design is utilized. I'll talk a little bit more about the reduced popcorning because it's actually a slightly different issue with these types of parts, and I'll get to that shortly. So why else? From an electrical, you know, perspective and a thermal perspective, if I look at thermal perspective first, theta JA for a QFN in every instance is better than a QFP, a TSOP, or a QSOP. So it actually gives you the opportunity to have a 2x increase in power dissipation through the package and the thermal pad. So, you know, a real benefit to using this type of part. The size of the package significantly reduces the inductance. And when you reduce the inductance, you get better RF performance or speed in the circuit. And again, here you can see the differences between a QFN and a TQFP, and it's again about 2x improved, so that this makes this particular part very popular in RF configurations. And then we get to the uh-oh part. So, it's obviously the next generation technology for consumer electronics, but is it the next generation packaging format for everybody else in the electronics industry? And we've done a lot of testing and worked with a lot of customers to, kind of determine what you need to do to make this type of package, bottom terminated component, more applicable to high reliability environments. So let's look at some of the challenges. Some of this you saw with Phil. What I'll go so far as to say is that when you're working with this type of package, you need to use non-solder mask defined pads in the configuration rather than solder mask defined. Part of what we've seen is when you use this type of configuration on this type of component, the solder mask actually acts as a choke collar. And so it becomes a stress location in the assembly of the unit that can result in a micro crack and actually propagating across this part of the device quicker once it's been installed. So, we understand why SM solder mask defined pads are used, but in this case, for enhanced reliability, we recommend steering clear. And you've heard some talk about vias in some of the questions earlier. The real issue, and I've been dealing with a customer for close to a year on this particular issue. I've got them from 49 holes down to 25, from 25 down to 4. I finally couldn't push back on his contract manufacturer in China anymore. They flat refused. They wanted the 4. So I said, okay, and we defined where they would go with respect to the window painting. But what happens is, when the solder wicks down, and you got to remind yourself that the thermal pad, because of the volume of solder, has significantly more surface tension than do the I/O joints. A lot more. So when it has an escape path, it's going to wick down the hole to some extent, and folks have said, okay, let's go to smaller vias so that the solder won't flow down. And what that does is it presents a challenge now for your circuit board fabricator with respect to the aspect ratio on the circuit board. So again, it's a trade-off. My recommendation is keep these as minimal as possible within your pattern, and if you can get away with it, plug them. It's the much better way to go for reliability. So what happens, and in this case I'll talk to this one customer that I've been working with, is the solder, some of it flowed down, and the thermal pad then pulls down against the part, and it actually pushes the solder out on the I/O pads. And we ended up with a bond line thickness of about 1 mil because of the amount of solder that flowed away from the thermal pad. 1 mil bond line translates to 0 reliability. And I'll show you some pictures, and I know Phil talked about it a little bit, but you need a bond line of at least 2 mils. My gut says you need at least 2.5. And so, if you use the old rule of thumb that if you put in 5 mils of wet paste, you're going to get about 2.5 mils, 50%. That puts you in the ballpark for getting the right bond line thickness. And for QFN or bottom termination components, that's an absolute. Another suggestion that was brought out was to print the window pane structure and then let's surround it with solder mask. Well, we just defeated the purpose of providing paths for the solder for the outgassing. So this wasn't the best way to go to help improve the solderability of these parts and provide the right bond line height. But it kind of shows people are thinking about it. So I think my numbers might be a little bit different from Phil's, but we talk, and from our testing, that you want to extend the bond pad beyond the perimeter of the component by 0.2 to 0.3 millimeters beyond the package footprint. you can see the considerable voiding. And the key point to voiding control, again, is just what we've been talking about, is the volume of paste printed, the window painting structure, the escape paths, how you work all of that in your design. Because if you need to have the thermal pad for thermal transfer purposes, the worst thing that can happen to you is to have your die right here and have a void right below it. Because again, that's going to create a thermal stressor point that's going to cause coarsening of the solder and possible breakdown prematurely. So trying to control that voiding is the #1 issue with these types of packages. And you heard a lot of talk about the window pane to do that. The excessive amount of paste can float the part, that's a given. The real key is to get 2 to 3 mils of post-reflow solder thickness. Sorry about that, I cut that off somehow. And look at the ratio of aperture to pad for your I/O configurations. What we usually see there is reducing the pad print on the I/O pads by about 1 mil in each direction. So if you've got a 5x10 I/O pad, you want to reduce it to 4x9. And you'll end up getting a reasonable height on the I/O joints as long as your thermal pad is correct. This was one that I had a customer call me up about a year ago, and he said, we're getting failures on 100% of our product, and which is not a good number. And so what we did was he sent me this over the phone. Well, just while we were on the phone, he sent me this in an email. And I said, I can see your problem already. And I kind of did the math in my head really fast, but I read the data sheet, and the data sheet says the solder paste coverage should be 40 to 80%. That's actually a pretty wide bandwidth. My recommendation usually falls somewhere between 65 and 80% coverage is going to get you to the right thickness for your bond line to be reliable. But if you do the quick math on this, 26%, guess what? His contract manufacturer in China could not read the English very well, but he could interpret that document perfectly. And so their stencils were this. Consequently, they had only 26% coverage on the thermal pad, and the ending bond line was 0.7 mils. And a 0.7 mil bond line thickness results in 100% failures. So be careful. Make sure that when you spec this out to whoever's doing your manufacturing, be it a contract manufacturer or internally, that everything in this regard is clearly understood. This is a picture that was shown earlier, but the real issue here is these parts are susceptible to dimensional changes as they go through reflow because of the materials that are used to make the LNCSPs. And in this case, we had a project that was for a military manufacturer who wanted to use these parts, and their supplier admitted to them that the package was more susceptible to moisture than they had originally perceived, and this resulted in a transient swelling of the part during reflow. And the transient swelling created this vertical lift that caused the solder separation that you see here. This was not popcorning. This was not like people have talked about with ball gritterate parts for a long time, where moisture in the part escapes through the bottom of the part during reflow and actually the vapor has enough force to drive one of the balls off the pad and create a short or create an open. This is actually swelling of the component. So some of the things that we've seen that have to be done with these types of packages is they have to go through some form of a bakeout, again, to help assure that you've minimized any kind of vapor in the part and reduced the swelling so that when it goes through reflow, you don't have this issue. So some things you can do. Very good control of your moisture sensitivity levels for these parts. Pay attention. Some of the things that we like to talk to people about is how should you set up your reflow profile for this type of part. And we like to see a 2 to 3 degrees C rise from room temperature to the preheat level. We want to preheat to at least 150 C. Then as you go to the ramp up into the spike zone, you want to increase that ramp up to about 4 to 5 C, and then cool down again, pretty much as the same type of ramp up that you had on the rising edge. That disagrees with the J standard. That's what we do. And where they say you can go up to 6 degrees per second. We just think that's too rapid and creates a scenario for failure. The other thing is that you want to make sure that you've got your part back down to around 60 degrees C before you do any cleaning processes, or you're going to get into some issues with the temperature changes there. So this is the kind of joint you want. 2.5 millimeter, 2.5 mils, I should say here. So about 75 microns. That's the thickness that you would prefer to get. In the left-hand one, you can see some of the voiding. And this particular QFN package, the I/O pads had castellations, very, very, very much like the old ceramic chip carriers. So you're able to get a fillet. And so you can see here, nice joint formation on the I/O pads, nice bond line thickness. That's what you really want to get with this type of configuration. This is a little bit more about what you probably don't want to get. If you push out the solder because your thermal pad's pulled down against the component, you get the bulbous joint along the I/O. Particularly because on most QFNs, the material on the I/O is not solderable around the perimeter of the part. So that actually, if you were to look down from the top, you would see that bulbous joint, and it's not connected to much of anything. So one of the things that is happening, and it's still relatively new, and I have no data on it myself, is that McDermott has come up with a material that can prep the surface, this point here, on these parts, and actually make them solderable, so that you have an opportunity then to create a fillet on these components. Jury's still out, so just want to make you aware that something is being done to enhance the solder joints on these types of parts. I hope it works, because it will be a benefit. The other thing we've done is kind of extensive analysis. It's been known for a long time that surface mount components can move during reflow and self-align. And so one of the things that we asked ourselves is, does that happen for LNCSPs, QFNs, and such? And what we were able to do, we've actually placed these parts 100% off the pad, which hopefully your robots won't do. But we did this on purpose, and we were able to see that it flowed back enough that this would meet IPC Class 2 requirements. Probably not IPC Class 3, but when you're starting a full pad width off to begin with, not bad. So in that sense, this type of part can help you improve your manufacturability. Board flexure, I'm going to go into a little more detail than Phil did. One of the things that we have seen is that when people do a circuit board layout, they put in test points. Where do they put them? Wherever there's room. Classic way to go. They put them where they've got a place to go on the board. And what we have learned, and I'll show you in my next slide, is that the localized deflections that can be induced by the pogo pins on an ICT fixture can create localized deflections on the surface of the circuit board that are sufficient to crack solder joints. So in other words, not a good plan. So we actually have a methodology where we can show customers where they might need to move those pins and locations to spread out the pressure that's being applied and minimize that type of an issue. One of the things that we've done, and again, this is a lot of testing, is that when you're using a SAC material, be it SAC 305, 105, or SM 100 type materials, is that you don't want to go above 500 microstrain with respect to the board flexure. And this could be board flexure from ICT testing, from depanelization, and Phil kind of covered that. You can get significant deflection there, and in every case you're going to get a scenario where you can crack a solder joint and it's not going to be immediately visible, and then you're going to get a failure. These types of parts, because you're working with a solder bond line that's 2 to 2.5 mils, are even scarier. So 500 microstrain, at least in our experience, seems to be an acceptable point. That's actually a very small strain level. So you have to be conservative when you're using these types of components. And again, IPC is looking at some specifications for this. How far out that will be, I'm not quite sure. I guess I did an IPC specification pretty close to 1 million years ago. IPC CM78, if any of you ever remember that, it was the first IPC document having to do with surface mount. And it took us 6 months to change printed circuit board or substrate to packaging and interconnect structure. Other than playing bridge with a couple of people, it was the closest I came to killing somebody. So since then, I just said, I can't do documents by committee. I said, they drive me nuts. But that's still the methodology. So here's that fixture type thing. Okay, you've got your circuit board mounted here. You've got your vacuum structure that comes down. You've got your pins that are, in this case, hitting the board from front and back. And what you get is situations where you can get these little micro changes in the board surface that are extremely localized and result in significant strain that can cause failures. So again, when it comes to ICT, be careful. This applies to more components, by the way, than just bottom terminated components. This can apply to any other component on the board. One of the other things when you get this kind of flexure, be it localized, is that you can get pad cratering. And this is a combination of either the ICT board depanelization, possibly connector insertion, shock and vibration type mechanical stresses that can occur. And if you've got a typical stack up of a board with a substrate, with the die, with maybe possibly a heat sink on it, you're susceptible to getting a crack underneath the solder of the circuit board, which is, for all intents and purposes, extremely difficult to see unless you do a cross-section. So what are the drivers? Finer pitch components. This is what we're talking about. We're going smaller and smaller and smaller and getting finer pitch. We've got more brittle laminates now that we've moved from tin lead to lead-free manufacturing. The medical folks are facing this right now. We're using stiffer solders, a SAC versus the older tin lead. And if we have a large heat sink involved, that becomes a fourth variable. So, die and pry, you heard, virtually impossible to help there. X-ray probably won't see this. Either will a shear test. So it becomes, identifying it strictly through cross sections, and so that makes pad cratering a very insidious type failure mode. So what can you do? Again, this is kind of counter to what I said earlier. Okay, is you can go to a solder mask defined pad configuration. You might have to limit your board flexure below 500 microstrain to be able to help with that. you might be able to change your SAC 305 to SAC 105. I don't know if you all are aware, but one of the data that we've seen and the data that we've worked with is if your application is mostly thermal driven, SAC 305 behaves better. If your application is more shock and vibration driven, SAC 105 behaves better. And we have extensive data on that on our website, and I'll talk about that in a moment. So you've got new laminate materials. Intel's been doing a lot of work in this area to eliminate it, but you know, they're trying to characterize some of these laminates using high-speed ball pull and shear. I don't know. I've seen some of the preliminary data. I'm not sure that they're on the right track, but we'll see. Another issue where the jury's still out. One of the things that we do say is that we need more information given to us when you look at the stack up of materials with regard to fracture toughness and the elastic modulus. This will help us to make some better determinations on the reliability. This is kind of what you saw a little bit earlier from Phil. What I want to kind of do is, you know, you've got the standard thing that he showed, QFP, 10,000 cycles, move down to a BGA, move down to the leadless CSP type configuration. And if I add flip chip out here as a fourth area, it's comparable to this. But if you look at, you know, you've got a 3x reduction approximately going from a ball grid array to this type of part, but it's driven by the die to package ratio. So if your die, like I talked about way early in the presentation, is 40% of the size of the package, 8,000 minus 40 to 125 cycles, and keep in mind that I talked about plus 85 here being equivalent to 24 cycles being equivalent to a year. So 8,000 cycles is a long time. If we then go to a die that's 75% the size of the package, that reduces by an order of magnitude to 800 cycles. So 800 cycles, if I divide that by 24, is that good enough for your application? Maybe. You'd be okay. When we look at the size of the package, same type thing. If I have a 44 IO package, I can typically see 1,500 cycles, and if I go a little bit larger to a 56 IO, it drops to 1,000. Again, you know, using that kind of rule of thumb, is that good enough? Might be for your application. If you figure out that it's not, maybe you don't want to use this type of bottom terminated component in your application. That's part of your engineering analysis. Cyclic bend. One of the things that this test does that's kind of fascinating is the fact that you start out looking at a 2 millimeter deflection, and you do 300,000 of them in a relatively short period of time to determine the mechanical toughness of the solder joints. And we've plotted here the differences. The beta is down around 1, which means that, you know, it's not at end of life, but it could be more attributed to you know, kind of an infant mortality type failure if you run into it. We did a lot of work with International Rectifier on a 5x6 millimeter device to come up with this. And what it kind of suggests is that you're experiencing, you know, a brittle failure of the solder on this type of device. Dendritic growths. Again, we talked about it earlier, and we've talked about bond line thickness being a critical issue. Because of this low standoff, it's very easy to trap flux underneath the component. And when you're using no clean flux, Phil's mentioned, you've got to really requalify that with respect to this type of package, because there is a potential danger that can lead to dendritic growth. We kind of see that, you know, when you're looking at like weak organic acids and total accumulation of cations and anions, that about 150 to 200 micrograms per square inch is about as high as you want to go before you're going to set yourself up for potential dendritic growth. With an aqueous cleaning process, one of the things that we've seen, and we've worked with several manufacturers on, is the classic temperature to do an aqueous clean is about 140 degrees Fahrenheit. Bumping it to 150 helps dramatically with removing materials so that you get better cleanliness. Adding saponifiers, an absolute, because of it changes the surface tension of the material, and I think that's something that you have to consider. The other is to change the number and the angle of the impingement jets that are in the cleaning system. One of the best that we've seen is a focused jet that comes straight down onto the board, and as it hits the board, bleeds out under components. It's a system manufactured by Austin American Technology, and it's unique in the industry. And when you're dealing with this type of package and other low-profile components, we've seen that it produces the best cleanliness. One of the other areas that you have to pay attention to during design, we're working with a customer that has this problem right now, is if you look at the linear technology component on the left, sizable difference between the location of power and ground. So the potential across these 2 points is significantly separated. However, the intercell part over here has power and ground on adjacent pins. So what that does is it sets up a structure where you can have a high potential across the small gap. And that high potential across the small gap can provide one of the elements needed for dendritic growth. Obviously, you need proximity, you need an accelerant, some sort of moisture or something in the circuit board, and typically a power applied. And that's going to drive the potential for dendritic growth. So when you're looking at any of these types of packages, pay attention to the electrical interconnect. We've seen, in this case, you can see that the dendritic growth in this particular scenario happened in 12 seconds. So, pretty bad situation. You can get self-healing. Essentially, if you turn on a significant amount of power, and some folks do this, they can actually kind of blow out the dendrite momentarily. And this can occur at voltages as low as 5 volts. And at room conditions, 25 degrees and 60-degree type relative humidity. This is due to the contaminants that may be left on the surface of the board. They are typically the chlorides and bromides that are part of a halide configuration. Weak organic acids and polyglycols. They can also add to the reduction in surface insulation resistance, but maybe not as much as either the chlorides or the bromides. We haven't seen in our testing any real difference in this behavior if you're using lead-free versus the older tin lead configurations. But for example, the last bullet here where you're talking about a tin zinc configuration, you throw zinc whiskers into the mix. So that can create a separate issue for dendritic growth. These are some of the levels that we like to see. And you'll notice if you go to the left, before going into things that are in the brackets, those are the points that DFR likes as compared to what the industry kind of publishes. So in every case, we are looking at, to be reliable and have less susceptibility, lower levels of these materials is required. And we see that if you look, again, tying back up to each of the different categories, is that you can see, if we look back up here at the chlorides and the bromides, that you can possibly get ECM issues above 2, and yet, the spec can go as high as 3 to 4. Down here, you can see that you, again, based upon assembled board or bare board configuration, bare board here assembled, and then looking at the weak organic acids, is that there's pretty conclusive evidence that with weak organic materials, if you go above 200, the ability to get some form of electrochemical migration is extraordinarily high. So cleanliness is something you have to absolutely pay attention to with these types of packages. And here, to add to your confusion, is that we kind of walk through this and look at it with respect to the different specs. So you've got information about cleanliness in IPC 6012 and J Standard 1. And they kind of say 10 micrograms per square inch of salt or equivalent. What does that mean? You know? So, you know, that creates an issue for you. They say that that results in a 2 megohm surface insulation resistance. We just think that's not the best way to go. That the best way to go is to determine your process in manufacturing with ion chromatography. And again, there's a lot of different ways to look at that with respect to the chloride and the bromide levels based upon a whole variety of different specifications. So I think, going back to the previous one, that, you know, if you pay attention to what we're saying, which are much more conservative levels, you'll be much better off. Some of the things to help you with utilizing these parts and mitigate risk is to perform a DOE on your stencil design. Getting that window painting structure on your part for your particular board is a critical piece of the puzzle. Check the reflow profiles for the ramps that I mentioned. Absolutely look at your board flexure and make sure that it's under 500 microstrain. If you move from a single row to a dual row type QFN or LNCSP like you see up here, you've added that much more difficulty with this type of component. And cleanliness is absolute, it's a critical. So some folks have actually gone as far as reballing this type of package, bottom terminated component, which, you know, is one way of solving the problem. You've created proper height, you can clean under the part, you've actually created a ball grid array, but you've defeated the purpose of the low-cost component. Again, you know, if that's what you need to do for your application, that works. The ownership of the second level interconnect is typically you, and that's where you've got to drive these decisions. And you actually need to be able to extrapolate to your needed field reliability. I need to survive in the field for 10 years. I'm going to see shock, vibration, temperature cycling. You need to take all that into consideration and look at this part with respect to that and make a determination that it's going to survive in your field environment. So with that, this is my contact information. I've got business cards here. I hope you'll come catch up with me at a break. A couple of things for you. If you go to our website, which is www.dfrsolutions.com,